Sorry, so my connection got broken. Really sorry. So we are already late by some minutes, so I'll start. So before starting, so I let me just check whether there has been any questions. Okay, so let me start. So I'll present my screen. So I am audible, right? So I hope I'm audible. And welcome to this course of chemical crystallography. So this is I think the fifth week, and by now, so you are we are familiar with the pattern. So every Saturday from 3 we are meeting. So just can you just send me a yes or something in chat box to let me understand if like I'm audible or not. Just like a simple yes or like I'm to just make sure that I'm audible. If not, then I'll proceed. Okay. Okay. So thank you. So as you all know, so uh, we are meeting every Saturday, and about the course. So if you want, yeah, okay, no problem. So you can just listen to it, or it will also be uploaded to YouTube. So from there also you can listen. So no issues if your network is not good. So you, as you all know, so if you have any questions, so you can post your question in this Ask a Question tab in the Swayam portal, and when the professor sees it or if I see it, so then we will try to reply to your question. Okay, so welcome to this live session 5 of week 5 of the course titled Chemical Crystallography. So by now we are all very familiar as to why we are studying this exciting technique. So this X-ray diffraction. So this is indeed a very exciting technique, and there are two ways in which we can do this. So the first is the single crystal XRD or SCXRD. So which the professor has started talking about. Uh, since this course is of 12 weeks, so as far as I can see, so in the first 10 weeks, so you will be taught about the single crystal XRD only, and then in the last 2 weeks, the professor will teach you what is known as the powder X-ray diffraction or PXRD. So basically, what is like single crystal X-ray diffraction? For single crystal X-ray diffraction, you have to have a single crystal, which is preferably like uh, uh, it has to be very large in size, large in the sense that even if it is like 500 microns up to 1 millimeter in length, and like 50 to 100 microns in the thickness and in the height, then it is like it can be called as a good single crystal, which will most probably diffract. And why this single crystal X-ray diffraction is very important, because using the single crystal X-ray diffraction, you can get the underlying structure, and you can just visualize the molecules as it is. If you have a stereo center in the molecule, so if you want to know, if you have made a tried to synthesize a pure enantiomer, so whether that center is a capital R or capital S center, whether it is a pure enantiomer or not, so you can get the actual structure using this single crystal X-ray diffraction technique. However, so the difference between this single crystal XRD and the powder X-ray diffraction is, if you have some, if your sample, which you can see it is diffracting, but it is not diffracting that much that you can get the underlying structure, or if it is made up of very small very small what size of the crystallites, then it will not be able to give the structure. However, so it you can take the powder X-ray diffraction of that sample, and then you can get some peaks. So those peaks will correspond to the HKL planes, which you have been studying now, and also you will study in the later weeks. So from the HKL planes, then you can also like there is some software with the help of which you can basically assign that, suppose this is my 100 plane, or this is my 101 plane, so you can assign the planes. However, you will not get the exact structure using the powder X-ray diffraction. But what you are studying now, so that is the single crystal X-ray diffraction, and for which, so this is the basically the schematic. So what we have is, so we have a crystal which is like it has to be like around this 500 microns or even less. Then if we shine X-rays on it, then there will be diffraction in all the directions, and then it will fall on the detector. So the detectors used nowadays is a charged couple detector, or a CCD detector, which is basically a area detector. So you can see here, so this is like a plane. So if you consider is that one axis as perhaps the x-axis, another is like the y-axis, so this is forming a xy plane. So this is the area detector, and the advantage of the area detector is that, as you can see from here, it can take many diffraction spots together. It can take many diffraction spots at the single time. So previously, when we did not have this area detector, so what we used to have is was called as the point detector. And so using point detector, so to take like one data, so for the one single crystal data used to take like 10 to 12 days, 10 to 12 days of continuous exposure of X-rays to the sample to get the spots, because point detector means there is only one point and it is taking the data. So it has used to take a lot of time, and that is why, so when the Friedel's law came, so it helped a lot, because as you know, so from Friedel's law, what does it say? It says that a diffraction space will contain a in center of inversion, irrespective of the fact that your crystal system has a center of inversion or not. So suppose even if your crystal is crystallizing in P1, that is triclinic space group, due to Friedel's law, you just have to take half of the Ewald sphere. So automatically, so from that one formula or one step, your 10 days data is reducing to like 5 days. Hence, this Riddle's law was very helpful in the previous days, but nowadays we have area detectors, and we can like take data in like from even from half an hour to like 2 hours to up to 10 hours. So that is the difference between the two types of techniques. And so we have discussed all this in the previous class, right? So your assignment 3, so we were discussing this. So it's how to understand the Miller indices. So what we have to do, basically we have to take the intercepts and then take the reciprocal of that. And as we know, so the reciprocal of 1 is infinity, and the sorry, the reciprocal of 1 is 1 and the reciprocal of 0 is infinity. And we also have Miller indices for crystallographic directions, for which we have to subtract the tail from the head. So we have learned all this. We have also gone through this slide where this we found that this is like a body diagonal, and then this is a phase diagonal and also the coordinates. And then I think we also covered this. So I think we were somewhere here that if we have a crystal lattice, then what will be the origin? So actually the origin can be like anywhere in the crystal lattice. So this was supposed to be true, and then we had another question. So I think we were discussing this question that if we have a cubic system, then this family of planes will include all of this, but this will not. So this was discussing. So if this is a cubic system, it will be true, but if we have a monoclinic system where or like even a tetragonal system, then this will so this is a tetragonal system where this axis is equal to this axis, let us assume, and this is not equal. So then this plane and this plane will not be equal. So then I think the next was this question. So that what will be the Miller indices for a plane with intercepts of 3 infinity and 2. So actually, so let us try to do this. So if I take my pen, so what are the intercepts given is 3, infinity and 2. So what has to be done? So it is basically the intercept. It means, so if I have my coordinate axis like this, such that this is the x direction, this is the y, this is my z direction. So it is like it's 1, 2, this is suppose my 3, and then in the y-axis this is like infinite, so we can't really draw it on the two-dimensional screen, and then on the z-axis it is like 2. So simply we have to take the reciprocal, 1 by 3, 1 by infinity, 1 by 2. Now what we have to do is, so we just have to clear the fractions. So what we have to do for clearing the so 1 by infinity will turn out to be 0. So I am continuing here. So what we'll do is we will take the what will be the LCM? It will simply be 6. So I'll just multiply it. 0. This is like, this is 0. 0 into 6. Oh, we can put commas in between to distinguish. So this then turns out to be 2, 0, 3. And then what should we put? So should we put this bracket or this bracket? So there are many kinds of brackets, like in crystallography. So we have first bracket, we also have second brackets, we have third brackets. So actually this one is used to designate planes. this is used to designate a family of planes, so like equivalent planes, and this is used for directions. I don't have the space to write. The directions. So this is what, so here we are finding out the plane, right? So the question says that the Miller indices for a plane with intercepts so and so. So sorry, so since this is a plane, so we will use the third bracket. So this one is the correct answer. Okay, so not this one. So we got this. Now we will come to this question. So then, so here for easy visualization, so already this is drawn. So the question was that the Miller indices, what is the Miller indices of the following plane? So this is very nicely drawn. So if we have a plane like this, where this is the x-axis, this is the y-axis, and this is the z-axis. So this is like convention. We conventionally draw this like x will be this direction, where you can see what is written is 1. This means that it is intercepting the x-axis at unit 1 unit cell length. So this is 1, and then this point is at the middle of the unit cell parameter along y. So this is my half, and then along z this is like 1/3. So then again, so this is like very simple. We have the intercepts. What we have to do, we just have to clear the fractions. So we have like 1, then so the convention is, so we have x, then y, then z. So at first we will have 1, then we will have 1/2, and we will have 1/3. So then if we just want to clear the fraction, no wait, so what is given is, so we have the intercepts, right? So if we go back here, so what we have to do is we have to identify the intercepts on the x, y, and z axis, and then specify the intercepts in fractional coordinates, and then what we have to do, we have to take the reciprocals of the fractional intercepts. So if we simply take the intercepts, sorry, if we simply take the reciprocal, so this will turn out to be 1, 2, and 3. So the reciprocal of 1 will be 1, reciprocal of half will be this, so this will be 3. So then again we have the same thing, so whether it will be first bracket or third bracket, but as we have seen from the previous slide, so this will be a third bracket because we are designating here planes. So it will be somewhat like this. So then again these are all the questions which was asked in the assignment. So the question was the plane representing the Miller indices 1, 1, 0. So this is now very simple. So this will be x, this will be y, this will be z. So the plane, so along x, the intercept will be 1 unit cell length. So we have this situation here. We also have this situation here. Now let us go for y. So along y also this will be 1. Now we can see if this is the y direction. This is cutting the y at 1. However, this is not cutting the y. This is parallel. Hence, and then along z, it is 0 means it will cut the z at infinity. So this one is the correct option. Okay. So then do you have any questions till now? Yes, yes, yes. When we have a plane which is not which is like not yeah, yeah, no, I'm just saying it because so if someone else has this question, so when they see the video, so when we have a plane which is parallel to some axis, then it means it is never cutting that axis. In other words, it is cutting that axis at infinity. Then if we take the reciprocal, it is becoming zero. So that's all. So then this was another question. So in the tetragonal space 2p4, which of the following is not an sorry. So which of the following is not an equivalent point? So can you tell me how to proceed with this? Hmm. Okay, so you tell me this first. So this is easy. So what are the intercepts of the plane with Miller indices 2, 3, 5? Yeah, why will it be 4, 6, 10? So here actually the Miller indices are given and you have to find out the intercept. That is also some network problem, I think, from my end. So this was another question, that what will be the stereographic projection of the point group belonging to ammonia molecule? So this is also a very interesting question. So what is the ammonia molecule? So let me first draw that. This is the molecule. So actually, we kind of draw it like it has a lone pair here like this. So this is, if we consider the nitrogen atom to be in the plane of this laptop or laptop screen, which we are seeing now. So this hydrogen is also in the plane. Now this hydrogen is in front of the screen and this hydrogen is at the back of the screen. So what is the molecular symmetry here basically? So at the first sight we can see that there is a C3, because if we draw a straight line from the top like this, then all the three hydrogens, so since all three are hydrogens, so they are equivalent and they are lying 120 degrees apart from each other. So 360 degree divided by 120 is 3. So at the onset we can say that we have a C3. Now after in addition to that, now we can see that we have a sigma v. Why? Because if we consider this plane, we consider this plane like this, then these two hydrogens are reflecting each other, so they are the mirror images of each other. So see, now since the C3 is also along this direction, the C3 is along this direction and the sigma v is also along this direction, this means that this will not be C3H, because H mirror means that it is perpendicular to the principal axis, but the mirror which we have here is like parallel to the principal axis. So we have the point, the molecular symmetry of the ammonia molecule will be C3V. Now if the let me write down C3V. Now if the molecular symmetry is C3V, then what will be the point group? Because as we know, point group is exactly similar to the molecular symmetry. When we talk about point groups, we have 32 point groups, and space groups are nothing but point groups added with translation, which is the main symmetry of a lattice, and then screw and glide, because screw and glide comprises of like screw comprises of rotation followed by translation, and glide comprises of reflection followed by translation. So along with the point groups, when we add screw, glide and translation, we get the space groups. But point group and molecular symmetry are used to denote the same thing. So if the molecular symmetry is C3V, then what will be the point group? So let us we first have to find out the point group here. So how to deduct the for at first we have this C3, which is like the principal axis. So at the onset we have 3, we can write 3. So if the principal axis is 3, then what crystal system it is? So this will actually be the trigonal crystal system. So we have 7 crystal systems now, and so apart except the cubic one, so all of them have like a principal symmetry. So as we know, so like for triclinic crystal system, the main axis is like 1. For monoclinic system, the main axis is 2. Then we have the orthorhombic. So for orthorhombic also, the 2 followed by the fact that we have that many perpendicular to, so like 2 to 2, where the corresponding molecular symmetry is D2. Then we have tetragonal. So for tetragonal system, the principal axis of symmetry is 4. For trigonal, the principal axis is 3. Then we have hexagonal. So for hexagonal, the principal axis is 6, or like C6. Right, and then cubic is separate. So cubic is higher symmetry. We have the tetrahedral and octahedral molecular symmetries for the cubic. Anyway, so here, so C3 turns into 3, and then we have V. So V simply means a mirror. So we will write M. So then this is the point group. Now once we get the point group, then we can easily find out the stereographic projection of the point group. So like instead of identifying so that which one it is, so what we have to do, we have to draw. But actually, so if we look at the two options, we can see that this triangle means that this 3, this is also triangle, but here these are not triangles. So at the first we can like say that these two are not. So among these two we have our correct answer. So if we have it, so let me just what is this? I'm just drawing it here, or maybe I can like draw it in a we have this here, and then let me first draw the C3. So for drawing the C3, so what is given here? So it's like an X kind of thing. So we can use anything. We can use like a small dot also, something like this. Yeah. So at first we will draw the C3. So C3 means we have this here, it will come here, then followed by here. Then if we have a mirror, then the 3 is like going into the screen of the laptop, right? So this is perpendicular, so for that we use, what we do use, we use a triangle, right? We can put a triangle to indicate that, and then the mirror will be along this. So we can have, we can imagine a mirror like this. If we imagine a mirror like this, then we, this point will come over here, and if this was on the top, then after reflection along a mirror like this, then it will remain, stay on the top only, because if it were a perpendicular mirror it would have gone down, but since this is a parallel mirror, this point will come over here and the top will remain on the top. This point will come here, then the mirror is continuing like this the whole place, so this will get reflected here, and then this will get reflected here. So then what is like this resembling? So this is resembling this one, right? Because here we only have the 3, but for ammonia molecule, yeah, so for ammonia molecule the point group is 3m, so this is the correct one, which means that we have this one. Okay, so then we finished this, then we have to discuss this, right? What are the intercepts of the plane with Miller indices 2, 3, 5? Now let us refer back to our slide. So what is the relationship between intercepts and Miller indices? So when we have some intercept on the XYZ axis, we have to specify the intercepts in fractional coordinates and then take the reciprocal of the fractional intercepts. Okay, so we just have to take the reciprocals of the fractional intercepts. Here what is the question? That what are the intercepts of the plane with Miller indices 2, 3, 5? So we have to go backwards, right? So when the Miller indices are given, so what we have to do at the first, obviously we have to take the reciprocals, right? So okay. So here the Miller indices are given 2, 3 and 5. So if we take the reciprocal 1 by 3, 1 by 5, then we have to take the LCM to get the intercept. So what is the LCM? So we have 2, we have 3, we have 5. So what we have to do, if we go from 10, it will not be divisible. 15, it will not be divisible by 2. Then we have 20, 25. So we have to go up to 30. If we go up to 30, then what we will get, 15, this is 10, this is coming out to be 6. So my intercepts means the point at which this plane will be cutting the x, y and z axis. So the intercepts will be 15, 10 and 6. Okay, so not 4, 6 and 10. So this was given to maybe to confuse you. So the intercepts on the x, y and z axis will be 15, 10 and 6. So this one will be the one. Okay. So actually next week I will not be there to take the live session, so I will be recording it beforehand. So is there anything specific which you want me to discuss, so then I can discuss that, because I will record it and upload it before I leave, because I will be out of station and I'll be in a place where there will be no network. So, do you want to me to discuss or to explain anything specific in the next week? So, please like unmute yourself and say. So, you have given submitted all your assignments. So, up to like assignment 4. Okay, so you have submitted assignment 4. So, week 4 is done, right? So then week 5 you are you can access the videos, right? Okay, okay. So in week 4 you have had the Miller indices only, and then the ceramic structures and all that, right? Atomic packing factors. Yeah, okay. So then, yeah, okay. Okay, sure. Okay, sure. So let me write that down. Nerve density, yeah, sure. So in the theory of X-ray diffraction, so you have had the basic, I think. Okay, I understood. I will make it accordingly. Okay, so then maybe we can stop here. Yes, yes, okay. Thank you. So if you have any questions, you can post here. Okay, so you can leave the call.